So this next section is called, well, it's not called much of anything. It's called vectors. You guys are familiar with vectors already a little bit if you've taken physics. If you're in physics right now, I'm not sure if you've talked much about them, but hopefully this won't be too bad. What do we know about vectors? They have a direction. So they have a direction. And what else? A length or magnitude means the same thing. Okay, so they look pretty much like a ray, which is what you learned in geometry. But in the right context, this could mean that we have a wind vector or a velocity vector pointing in that direction with a certain velocity, 30 miles per hour or whatever the case is. Okay. Let's talk about the notation. In math, we like to try to clean up the notation as much as possible. I think I actually observed a couple of physics classes. You guys did like X and Y components and had this big table and all this other stuff, if I remember correctly. We're not going to go do that much. Okay. So here's the notation. Let's say that this point here is called P. And this point here is called Q. Okay. You could write this as vector PQ, and you just put a little ray over it. Okay, and the order in which you write these letters is very important. Okay, we'd say that this vector starts at P and ends at Q, so that's exactly what you do in the notation. Okay, this is called the initial point, by the way. And where it ends, in this case Q, is called the terminal point. Now, sometimes, instead of using initial and terminal point in the notation, you might see a little A labeled here on the side. Okay, in the book, you're going to see lowercase and bold letters. That usually indicates that that is a vector. Okay, we would just write it, instead of you drawing over the A several times and making it bold, you just put a little line over it. So you can call this vector A, you can call it vector PQ. And now as far as the length or magnitude, we just put vertical bars on the side of the vector. So you could write it like this, or if you're just talking about A, you can write it like that. This does not mean absolute value. In the context of vectors, this means the length of vector PQ and the length of vector A. Okay? Any questions so far on just the idea behind a vector, what it is, how to write the notation? Yes?
So is a vector a ray?
Well, and geometrically they look like rays.
So not rays?
No. Because rays in geometry have a starting point, and the arrow indicates that it goes on towards infinity. So they don't actually have a length. So even though we're writing them so that they look like rays, it does actually stop here. Okay? Yes?
Is writing A the same thing as writing PQ?
Yes. As long as you have the little vector notation on top. Okay? Anything else? Okay. Just to get you an idea of vectors. Okay? So let's do a little intro before we start talking about some properties. Imagine that you have, let's see, what's a good example of something that's somewhat frictionless?
Ice.
Ooh, how about those, what are those tables called? You know what I'm talking about?
Yes.
Air hockey.
Air hockey.
What those things called?
He knew what I was talking about.
You'd probably be really good at like.
All right, so let's say we have the puck here, right? You know how it's got little friction on there, and it's kind of like sitting right above the surface there, and if you touch it at all, it's going to move pretty easily, right? Now, let's say that, and keep in mind we're not actually hitting the puck, but let's say that there's some kind of wind or some kind of force that's pushing it this way, and then another wind vector that's kind of doing that. Let's say that these have the same length. What's going to happen here? It's not going to move. If you understand that, you understand vectors. Okay? Here's another scenario. So let's write this down. No movement. What if, same idea, we have two different fans or something like that. One's pushing this way, and then we start one down here at the corner so that it's actually kind of blowing in that direction. Which way is it going to move? Towards the right, like this? And up. Very good. So you combine these two vectors. Does that make sense? So in the end, maybe it looks, maybe that's how it moves. Up and to the right. Does that kind of make sense? Okay. Now, what if, last scenario, we have two fans right next to one another with the same exact speeds, kind of doing that to it. What's it going to do? Move to the right. Okay. We call these, by the way, parallel vectors. And now, if you kind of understand what's been going on, we can actually define what parallel means. Parallel vectors, how do we know if that they're parallel? Well, they could be.
The same slope.
That's all good stuff. Same slope, equal value. Okay, let's combine using this idea that vectors have directions and lengths.
Direction and length are the same.
There you go. Very good. So parallel vectors, same direction and equal length. Okay, so if we have P to Q and A to B, may not be perfect, but we can say that these are parallel because they look pretty much the same length and they're pointing in the same direction. So here we would say that PQ is actually identical to vector AB. Okay? Any questions? So yes?
Would you need to have the lines like you said?
No. Now we could talk about magnitudes being the same, but if we did the magnitude, like if we put lines around this and said magnitude of PQ is equal to magnitude of AB, then they could be pointing any direction as long as they have the same length, so they wouldn't be parallel. That's a good question. Anything else? Okay. So going back to this air hockey example where we have two different vectors and we said, well, it's going to kind of move in this direction. Okay, that's actually called vector addition. I know you've probably done this a little bit in physics already. Okay, so let me show you how this works. It's actually a very visual and geometric process. There's not much work involved. You just have to connect things. Okay? Tomorrow we'll actually hit the algebraic properties and how to actually calculate stuff. Today, we're just going to talk about it and talk about where it starts, where it ends, that kind of thing. So let's say that this is U. And let's say V looks something like this. And the question is, what does U plus V look like? So if I wanted to actually, kind of like the air hockey example, combine these two vectors and see what the final motion or the final direction is going to look like, what do you guys know from physics? What can you do? How?
You add the lower unit is the one that's bigger.
Let's talk about this second vector for a second. Okay. We're gonna say that U is fixed, so we're not gonna touch U. Okay. If we want to combine U and V and add them together, what we're gonna do is essentially slide this vector V over to where U ends. I think they call this tip to tail. Sound familiar? And then just make another copy of V, which we can do because as long as it's the same direction and same length, it's the same vector. Okay, so does everybody kind of see what I've done there? We've taken the second vector, and then all we've done is connected it to the end of the first one. Okay, so now the answer is here. We connect from initial point to our new terminal point, which is right here, and we say that this green vector is U plus V. Does that kind of make sense? Yeah.
Okay, but why should we do that? Because if there's an arrow, wouldn't that like move it keeps going?
That's what we just cleared up. This, even though it looks like a ray, it doesn't keep going. It's a finite. Yeah, it's a finite length. It's going to stop where the tip of the arrow actually ends.
So why is there an arrow?
To indicate which direction it's pointing. If we didn't have an arrow, then it would be ambiguous and it would have just a segment, and we wouldn't know which way the motion is pointing.
Ah, yeah.
Does that make sense?
Yes.
Okay. All right. Let's do U minus V real quick. Okay, so it's going to kind of complicate the picture a little bit, but I think it'll make sense. This minus sign, what do you think that does to the direction? Yeah, it just makes it opposite. So if V, when we connect V to U, if this is the normal direction, then minus V is going to be the exact opposite. Does everybody buy that? Okay. So then where's the answer? On the left, from initial to the new terminal point right here, this would be U minus V. Okay, we're never really going to make anything this complicated, but I just kind of wanted to illustrate a point. You're going to add and subtract vectors the same way. You connect them from tip to tail. And if it's adding, you just copy the direction. If it's subtracting, you make the direction opposite. Okay? And that's it. Let's see. A couple more notational things, and then we'll actually do a couple problems here. What does this mean? This means, very good, it's the length of U plus V. So if you had to figure this out, you'd kind of have to do something like this, where you connect the vectors together, you draw in your answer, which is U plus V, and then you find the length of this u plus v vector. That's what this notation means. Okay? Before we actually start computing things and talking about numerical examples, are there any questions conceptually about what vectors are and how to connect them and add them and subtract them together? Okay. So here's a typical problem for you guys. Let's say A is at 3, 1, B is at 9, 7, and we want to, let's just do a few things here. Let's say you want to find this. Okay. First, what does this notation mean? What are we looking for? The length of the vector from A to B. Okay? We'll draw a picture first, and maybe you'll see that you don't even need it once you get used to this. So 3, 1, let's say that's here. Here's A. B is at 9, 7. So here's B. Where does this vector start? So it starts at A, ends at B. And all we want to do is find the length, or the magnitude. So what do you think we can do? Pythagorean theorem, distance formula, however you want to do it. Okay? If I did the distance formula, that would be the square root of what? What is the formula? x2 minus x1 squared. So 9 minus 3 squared plus, and then we just do the difference in y's, right? y2 minus y1 squared, so 7 minus 1 squared. 9 minus 3 is 6. Square it, 36. 7 minus 1 is also 6. So that's 36. That's root 72, which reduces to what? 6 root 2. Very good. Okay. Questions on that? Pretty easy, right? All right, let's add a part B to this. Let's say that we have P at 0, 7 and Q at negative 1, 0. Question, or yeah, let's do that. Find initial and terminal points of the vector AB plus the vector PQ. Okay. So I'm going to briefly cover up my answer for A a little bit so we can kind of look at the same graph. Let's draw PQ in here so we can kind of see what's going on. So PQ is at 0, 7, or P is at 0, 7, sorry. Q is at negative 1, 0. So this vector starts at P, ends at Q. So draw from P to Q. Okay, and if you're wondering what is the best way to add these things on paper if you have like coordinates and stuff, okay, if you actually count the rise and run of the vector that you're adding, it usually helps when you're connecting it. And here's what I mean by that. So if we're starting at P, in words, how do we describe what we need to do to get from P to Q? Down 7, left 1. Does that make sense? So PQ, we're going down 7, left 1. So if I want to copy that, you know how if we add vectors, we got to move this point over so that this vector slides over. Starting at B, it's going to end up with the terminal point down here somewhere. Well, just copy the motion. Starting at B, go down 7. So we're already up at 7. You guys see that, right? So from 7 down 7, where are we now? We're at right here at 9, 0. And then what else do we do? Left 1, so now we're at 8, 0. And if I connect B to the new point there, this vector and this vector are the exact same ones. Does everybody see that? So now where's the answer? Where's my initial point? Initial point is A. So what are the coordinates there? 3, 1. And terminal is where I ended up after I connected these two vectors. So if I actually drew it in, here is PQ plus AB. And what are the coordinates? Oh, did I switch the order? Yes, I did, and that's actually very important. I'm sorry, guys. Switch this around. These should be flipped. I'm not going to mess with it too much since I have very little space up here. But this actually is AB plus PQ. Okay? And what are the coordinates for the terminal point? 8, 0. Okay? So there's one comprehensive example, adding vectors together, finding lengths. Let's do the last one. What if I wanted to find this out? What does this mean? Oh, you guys can't see that. Yeah, so if I say find the length of AB plus PQ, we've already done the hard part. We're supposed to connect the vectors, figure out where one starts and where the new point is, where it ends. And now we can just do what? Find the length from where to where? From A, so our initial point, and this is our new Q, right? So distance formula. All we're doing is finding the length from here to here. So we've already added them up. If you have a good picture, you can kind of see that the difference is going to be 1 and then 5. If you don't have the picture good enough, as long as you have these points correct, you can do distance formula. Gets you the same answer, which is 25 plus 1, so root 26. Okay. I'm good, right?
Yeah.
Okay. Okay. All right. Questions on that? All right. Let's do more of a physics-ish example. What's that? Why wouldn't it? It always looks like what I do.
Well, we snapped.
You know, sometimes you're asked to take skills that are taught and apply it to new problems. That's part of learning and getting better at something. So it's not going to be literally the same problems, but it'll be involving the same kind of stuff. All right. Let's say we have some object here. And I have a force, which we'll call F1. Not a forest, a force. And let's say that this is 20 pounds. So maybe someone's pushing on an object in that direction with that much force, and then maybe someone's pushing this way. And let's say that this is at 13 pounds. And let's call this F2. So typical question would be to compute the resultant force and direction. Okay, well, to do that, we just want to add the vectors together and see where the answer is. That's the resultant. So how do I add F1 with F2? Yeah. So all you do is slide F2 over so that now we connect it with F1, and it looks something like this. And this should make sense. Remember the air hockey example, right? If we have a bigger force pushing that way and then a little one pushing that way, it's going to move up and to the right. Okay? So the green vector, that's our answer. Okay, so we want to find out two things about this green vector. We want to know what the actual resultant is, meaning how long that green vector is. And we also want to find out a direction. Okay? Well, what do you guys notice here? What kind of triangle is this? It's a right triangle. Let me redraw this so it's not so cluttered together. It's a right triangle. How long is this bottom side? What was the force in that direction? 20. What was the force in the vertical direction? How can we find the length of this? Pythagorean theorem. It's just finding the length of the hypotenuse. So we do the square root of 20 squared plus 13 squared. And then, I don't know what... Oh, that's hard to see. We got that light coming in. Yeah. How do we know? We're assuming that that is perpendicular. Oh, let me just slide this up. Ugh. Yes. Yes, you'll know that is a right angle. Yeah, that's a good point. Anybody have what that is, by the way, approximately? We're going to end with this example. So we got to find an approximation for this, then we got to find a direction. Square root of 569, which is, you know what, let's pretend that doesn't reduce since we're almost out of time. There it is. Now the direction. The direction just means, hopefully we can find an angle that tells us, you know, how much we've rotated from the horizontal. How can we find that theta? SOHCAHTOA. If we do tangent of theta, opposite over adjacent would be 13 over 20. Do the inverse tangent. And I do need your help here because we got to make sure we write this up very nicely. What is that when you take the inverse? You know, if you guys don't pack up right away, we can finish sooner.
I got you.
I know some of you are packing up.
I got you.
33.02 degrees. Okay, so here's how we would say this. We'd say that the direction is 33.02 degrees. There's two options. With respect to positive x-axis, or you're probably used to this from physics, which direction is this pointing? East, and we're talking north of east. Does that make sense?
Doesn't matter. Which one do you prefer?
Doesn't matter to me. Everything's legit. Okay? This makes perfect sense. Positive x is pointing east. So if you say with respect to that, we assume we rotate counterclockwise like we do with trig. If you say 33 degrees north of east, that means the exact same thing. All right, homework is day 4. I'll see you guys tomorrow. Oh, and ACT, don't forget about that. ACT is due tomorrow.